Okay, we're going to do the volume of prisms. We recapped it in the last lesson, some language to do with prisms, and I'll talk through them in a few moments. Just a quick recap. I was going to try and do this more practically, that's why I'd asked for you to get cans and jugs and things. I'll put up on Friday the video of why we're not going to do that today. The number of problems I had getting anywhere near accurate results basically meant it wasn't a good demonstration. So your homework will be on Friday, or your investigation on Friday will be to watch that video and come up with improvements, what things went wrong in and were limiting the accuracy I was getting in the volume measured when I was trying to do various cylinders and cuboids. So you will see the fun. You'll see the mess I made. I kept it reasonably tidy, but I did make a mess. Okay, let's start off with the starter question. What do we mean by area? What do we mean by volume? At its most basic level, area talks about how many squares would fit inside the shape. So I've got in this 1, 2, 3, 4, 5, 6, 7, 8. So the area of this is something to do with 8 squares. Now, it's fairly standard that these squares are single units, so that we can say this is 1 centimetre in each direction. When we multiply the 1 by the 1, that doesn't change my value, and the centimetre times a centimetre is centimetres squared, because that was 2 centimetres, 1 in each direction. Comes on to circles, a little recap. You should be able to calculate the area of this circle in a minute easily, so we can calculate it using the area equals, and if you remember the dance, pi r squared, sounds like area to me. The radius of this circle is 3. So when I'm doing my calculation, the area is pi times 3 squared. Now, before we come on to that, people are saying, oh, where are the squares? Well, we've got whole squares inside. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 squares inside. Then after that, what you often do to calculate shapes is go for the ones which are clearly more than half. 1, 2, 3, 4, 5, 6, 7, 8. And the ones which are clearly more than half, you assume there's enough small ones left over that will make up the difference. So that at the moment we've got whole squares, 16. And we've got 1, 2, 3, 4, 5, 8 over half. So that is actually, we're going to count those as they are. And then pair off all the other ones which are about half. So these are clearly over half. The about halves, we're going to count them in pairs. So we've got 1, 2, so that's 1. So I found there 4 pairs. Each of those pairs I'm going to count as being 1. So we've got a total of about 16 plus 8 plus 4, and the total area is estimated as being about 28 units squared. In this case, we're going to talk centimetres squared. You should be familiar enough with using a calculator for the area. So we'll calculate this area as being pi times the radius squared. And that's 28.7. 28.27. So we've just done a quick recap of what area is. It's about counting squares. So the question becomes, well, what happens when we're measuring volumes? Well, volumes is how many of these standard 1 centimetre cubes would fit inside a shape. So I've got the same basic shape, but now in 3D, as we did above. So there are 8 squares on the end. So the end which is called the cross. Oh, before yeah, we'll talk about volume when I come back in a minute. So the end area we just saw above is 8 centimeters squared. Now, and therefore, if there's only one cube deep, the volume is we've got 8 cubes in one layer. Okay. Now, one of the things we need to think about is what was special about using a cuboid. And hopefully you should be familiar with this tool from investigating prisms and pyramids. What actually makes something be a prism is when you cut across the shape at right angles to the lines. I just had to switch the application to one which is actually working. When I move this slice up, that's the bottom, and you can now see the shapes, both of them as being the same as this triangle. Same width, same height as this triangle. As it cuts up, on a prism, we see exactly the same triangle directly above each of the nodes. So each of these vertices and the vertex of a slice, they're always in line with each other as we move up. When we look at the pyramid, notice the shape stays similar, which means the ratio of lengths between two sides is constant. The shape stays the same, but its size changes for a pyramid. So a prism, the shape stays exactly the same. For a pyramid, the shape gets bigger or smaller as you roll up. So as we get towards the top, I've still got the same full-size triangle in my cut. And it doesn't matter what the shape is. Let's go for something up here. Let's go for a hexagon. All the way up, I see on the prism the same shape, and on the pyramid, the pyramid shrinks. Okay. Let's go for a few more. There we go. So my shape stays the same for a prism as I go through. Okay. So the shape stays the same as we work our way through. So as it stays the same, each time we get a new layer, each time we get a new layer of our shape, we will get another 8 cubes. So there's my first grey one. Let's just put in another layer of the same number of blocks. So I've got 8 in the first one. I've now got another 8 in the red. Let's go to orange. Each time I add a layer, I'm adding another 8 blocks. So we've got 8 in the grey. In the red, we've got another 8, that's 16. In the orange, we've got another 8, 24. Let's go to pale orange. Got another 8, 32 blocks in that shape. If you want, you can make up this shape. The link for this tool is actually in the notes. And what I can do is I can actually rotate it around so I can see, oh, it didn't line it up properly. I'm on the wrong plane. So it looks right in this one. When I quickly started adding them on, it didn't bind it to that block for some reason. But we've got the shape. So for 2 layers, which was red, that's 2 layers. We had 2 lots of 8, which was 16 centimeters squared. The orange one, that was 3 layers. And remember, these layers are of cubes. So we've got 3 times 8, which is 24. And I can keep growing it up. This final one, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 layers. Let's do it in blue. Blue. 9 layers. Each layer is 8 cubes, so it's 9 times 8 cubes. 9 eighths, 72 centimeters cubed. 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 The reason for the cubed is this area here is a centimetre squared. This length here is a length in centimetres. 1 centimetre coming back. Centimetres times something squared. If they're the same base, gives me centimetres cubed. Yes, I made a slight mistake with those previous ones. Okay, so that's the basics of the volume of a prism. You take whatever it takes to make up one end as an area, multiply it by 1 to say how many cubes there would be on that end, and then take that and multiply by the length. So let's just do it quickly for a couple of prisms. I'll do 2 versions with each one. Let's start with this one, which is, remember, a cuboid. Cuboid is a rectangle on the end with a length going back at right angles. Okay. We're looking for the area of the end, what's called the cross section. When we're talking 3D, we have cross section. So the area on the section, this is where in Russian you talk about S section. We will use S in a few lessons on area. So the area of the section of this shape is, if I say that's 3, that's 4, and that's 8. And we're talking meters cubed this time. Remember, units must be the same units. Always convert units to be the same. So length should all be in centimetres, metres or kilometres or whatever, but they must be the same. So the area of the cross section is 3 times 4, which is 12 metres squared. And then the volume, how many metre cubes can fit going backwards? Well, there's 8. So we've got 8 going backwards, the length, and we multiply it by this cross-sectional area, the number of squares that would fit in this first face. So I'd have 12 cubes in the first layer, 24 in 2, 36 in 3 layers, and in 8 layers, 8 times 12 is 96 meters cubed. General form, we've got A times B, the 2 sides on the base, and the length. So the volume is, for a cuboid, is A times B times the length going backwards. People use different letters, they use length, width. I'll stick to using fairly standard lettering. Right, so what happens when we come onto a triangular prism? It's still got the same shape going backwards, so identify the cross section, triangle in this case. And this time I need to know how to calculate the area of the triangle. Area of a triangle is half the base times the height. So I need the base, which I'm going to say is 4 centimeters. Perpendicular height, I'm going to say, is 5 centimeters. Notice perpendicular height. Next couple of lessons we'll be talking about this slanting height and how we can calculate it next week, to do with finding the areas of shapes. But this height must be at right angles to the base. So the area of my cross section, area of a triangle, is 1/2 times the base times the height. 4 times 5, 20, times 1/2, 10 centimeters squared. And again, to get that, turn that into a volume, I need to allow the length going backwards, and let's say 7 centimeters. So this tube has a volume, which is my length going back, 7, multiplied by 10, which is 70 centimeters. and because it's length times an area, length times area, centimetres times centimetres squared, the volume is in centimetres cubed. Let's generalise that one. So we've got the base, the perpendicular height. I always like to show it's perpendicular by putting the upside down t, and its length. So V is 1/2 the base times the height times the length going backwards. There's a reason I've written these in this form, because we're going to generalise it in a minute. Next two, cylinders. Cylinders are really just prisms. They've got the same cross section all the way through them. The cross section this time, area of the section, in this case is pi r squared, so you need to know the radius at the end. Let's make it on the outside. So the radius, I'm going to say, is 4 millimeters, so it's a pipe. So the area of the cross section is pi times the 4 millimeters on the center squared. Remember, area of a circle, pi r squared sounds like area to me. Yes, I will be annoying with that song. Now I need a calculator to do it. So I need shift pi multiplied by 4 squared. Oops, I didn't do the shift properly. Shift pi times 4 squared. Syntax error because it doesn't like the multiply afterwards, and it took it out. Shift insert multiply. And I get 50.27. So I'm going to say 50.2. 1 decimal place on an area. Let's say 0.3 millimeters squared. And the length going back on it is, well, let's say this time it's 12 millimeters. So this is a tube, 4 millimeters on the inside. What's the volume a 12 millimeter length would contain? So the volume is equal to the 12 millimeters I've got multiplied by my cross-sectional area, and that will give me an answer in millimeters cubed. So I'm going to use my answer. I'm going to do 12 multiplied by the answer from the previous one, the 50.3. And I'm going to get a more accurate answer than I would have done just typing 50.3 in, of 603.2. Okay, let's quickly whiz through the formula. We needed the radius on the end, the length going backwards, and the volume for this is the area on the section, pi times the radius squared multiplied by a length. Now, my first demonstration was based upon rectangles, which had a funny shape. You have this funny section going backwards. As long as you can calculate the area on the end, you know the cross-sectional area. So it doesn't matter what the shape is. If I know this cross-sectional area, and I know how long something is, I can always calculate its volume. So there's my cross-sectional area, and a general formula is the volume is the area of the section multiplied by the length of the shape at right angles. It should be at right angles to this area. Okay, so any direction I go on from this line, this area must be measured in it. So the area of the section is the area of that end piece. It must look the same all the way through, and that will calculate the volume of a prism. Okay, that's the end of that lesson. Go and do some whichever exercise is set. I think it's going to be a bookwork one this time.